Deep beneath the public galleries of NASA's most famous centers, behind doors that require clearances beyond top secret, there exists a different kind of archive. This is not a museum of past triumphs, filled with moon rocks and retired space capsules. Instead, imagine a vault safeguarding something far more potent: the blueprints for tomorrow. For over half a century, while capturing our collective imagination with lunar landings and Martian rovers, NASA has been conducting a second, silent mission. This parallel program has tested revolutionary technologies so advanced, so paradigm-shifting, that their very existence has been kept in the deepest shadows. What you know about space exploration, the public achievements we all celebrate, is merely the tip of a vast and hidden iceberg. Today, we are opening that vault. This journey will uncover 22 of these hidden innovations, concepts that sound like they belong in science fiction, but have been the subject of serious, classified research. We are talking about propulsion systems that manipulate gravity itself, materials that can bend light to achieve invisibility, and methods of communication that defy the speed of light. But this is more than just a list of incredible gadgets. We will delve into the compelling reasons why such world-changing ideas are kept secret, from national security concerns to the sheer challenge of explaining physics that borders on magic to the public. We will explore what these technologies reveal about our true trajectory as a species, hinting at a future where humanity's reach extends across the solar system and beyond in ways we are only beginning to grasp. Most startling of all, we will consider how the ripple effects of these hidden tests might already be subtly influencing the technology in our daily lives, hinting that the future is closer than we think. So, prepare to question everything you thought you knew about the limits of engineering and the pace of progress. What you are about to discover suggests that the grand story of human innovation has entire chapters that have been deliberately omitted. This is our journey into the classified archives, and it begins now. To truly grasp the significance of the technologies we are about to explore, we first need to understand the environment that keeps them hidden. Think of NASA's public achievements, the stunning images from the James Webb Space Telescope, the Perseverance rover drilling on Mars, as merely the visible tip of a colossal iceberg. It's the part we all see and celebrate, but beneath the surface, hidden in the cold, dark depths, lies a massive and intricate structure of research and development, a world of advanced concepts that never see the light of day. This separation isn't accidental. It's a deliberate and carefully managed strategy rooted in several powerful motivations. The most compelling driver for this secrecy is, without a doubt, national security. When an agency develops a propulsion system that could render current missile defense systems obsolete, or a material that could make an aircraft virtually undetectable, that technology instantly becomes a matter of the highest strategic importance. Its open disclosure could fundamentally shift the global balance of power. A breakthrough in energy generation or communications in space could create a military advantage so significant that it must be protected with the same vigilance as the most classified weapons systems. This isn't about hiding the truth from the public for its own sake. It's about preventing potentially disruptive technologies from falling into the hands of adversaries who could use them against us. Beyond the immediate concerns of national defense, there is the relentless pressure of the modern space race. While the Cold War rivalry with the Soviet Union has evolved, competition is fiercer than ever, now involving not just other nations like China, but also immensely powerful private corporations. In this high-stakes environment, operational discretion is a necessity. Revealing the exact direction of your research is like showing your hand in a high-stakes poker game. It gives your competitors a roadmap to catch up or even leapfrog your efforts. By keeping certain avenues of exploration confidential, NASA and its partners can maintain a crucial technological edge, ensuring that the next giant leap for mankind is taken by the United States and its allies. There is also a more subtle, yet equally important, factor at play: public perception. Some of the concepts being tested in classified settings are so far beyond our everyday understanding of physics that announcing them prematurely could trigger widespread skepticism or even fear. Imagine if NASA held a press conference to announce it was experimenting with warp drives or zero-point energy. The scientific community might dismiss it as pseudoscience, while the public could react with anxiety about technologies they don't understand. A culture of compartmentalization allows researchers to do their groundbreaking work free from the intense scrutiny, doubt, and potential backlash that could stifle innovation before it even has a chance to prove itself. This controlled environment ensures that only well-vetted, demonstrable successes ever make it to the public eye, preserving the agency's credibility while allowing radical ideas to mature in secret. This layered approach to secrecy, where information is shared on a strict need-to-know basis, creates a firewall within the organization itself. An engineer working on a revolutionary life support system might have no idea that their colleague in a different, secured building is testing a new form of propulsion that would make that life support system essential for interstellar travel. This compartmentalization isn't just about keeping secrets from the outside world. It's about managing the flow of information internally to protect the integrity of each individual project. As we now turn our attention to the specific technologies themselves, holding this context in mind will transform them from a simple list of wonders into pieces of a much larger and more profound strategic puzzle. Now that we understand the why behind the secrecy, it's crucial to pull back another layer and examine the how. The term hidden technology might conjure images of a single locked file cabinet labeled top secret, but the reality is far more nuanced. Secrecy isn't a simple on-off switch. It operates on a broad spectrum, and where a technology falls on that spectrum tells us a great deal about its true nature and potential impact. On one end of this spectrum, we find what we might call the quietly shelved. These are technologies that are hidden not by a deliberate act of classification, but simply by a lack of publicity. Imagine a team of brilliant researchers working for years on a novel approach to, say, growing food in microgravity. They might hit insurmountable technical hurdles or find that a simpler, more conventional method proves more reliable. The project reaches a dead end. From NASA's public relations perspective, there's little value in announcing a failure or a curiosity that didn't pan out. So the research report gets filed away, an experimental dead end that never justified a formal announcement. This isn't a sinister cover-up. It's the normal, bureaucratic outcome of thousands of research paths explored across a massive organization. Many of the items on our list might fall into this category: fascinating ideas that were investigated, but ultimately abandoned for practical reasons. Then we have the middle ground of the spectrum, a gray area involving corporate proprietary secrets. A significant portion of NASA's advanced work is not done in-house by government employees, but by private aerospace contractors. These companies, like Lockheed Martin's famed Skunk Works or Northrop Grumman, are hired to solve specific problems. In the process, they often develop groundbreaking manufacturing techniques, unique material compositions, or specialized software. This intellectual property doesn't automatically belong to NASA. It remains a trade secret of the company. The agency gets to use the final product, a new heat shield, for instance, but the precise recipe for how it was made is considered a corporate asset, guarded to maintain a competitive edge in the marketplace. So, a technology can be hidden from the public not because it's classified by the government, but because it's a commercially valuable secret held by a private entity. This creates a complex web where the line between national security and corporate advantage becomes blurred. At the far extreme of the spectrum lie the truly classified projects, often referred to as black programs. These are not shelved ideas or corporate secrets. They are active, highly protected initiatives with substantial funding and a clear strategic purpose. Access to these programs is restricted to a small number of individuals with special security clearances, and their existence is often not acknowledged by the government. The funding for these projects is frequently funneled through the classified budgets of other agencies, like the Department of Defense, making them nearly invisible to public oversight. This level of secrecy is reserved for technologies that represent a genuine paradigm shift, capabilities so advanced that their disclosure could compromise national security or provide an adversary with an irreversible advantage. These are the game changers, the technologies that could redefine everything from warfare to energy production. Understanding this spectrum is absolutely vital as we dive into our list of 22 hidden technologies. It allows us to be more discerning. When we discuss a concept like advanced field propulsion, we need to ask, is this a shelved paper study from the 90s, or is it an active black program? When we look at metamaterials for camouflage, are we talking about a corporate patent held by a defense contractor, or a fully operational capability within a classified spacecraft? This framework helps us separate the intriguing scientific what-ifs from the technologies that are likely already being tested in secure facilities, shaping our future from behind a veil of silence. As we explore each one, we'll weigh the evidence and consider its most probable place on this spectrum of secrecy. Now, let's dive into the first and perhaps most profound of these hidden technologies, a concept that strikes at the very heart of physics as we know it. We are all familiar with the fundamental principle of rocket propulsion. For every action, there is an equal and opposite reaction. A spacecraft burns fuel, expelling mass out the back to thrust itself forward. It's a powerful but incredibly inefficient system, shackling us to the need for enormous amounts of propellant that limit our speed and range. But what if there was another way? What if a vehicle could move not by pushing against anything, but by essentially bending the rules of the universe around it? This is the revolutionary premise behind the Flux liner and the field of advanced field propulsion. Imagine a craft that generates its own gravitational field, not as a byproduct of its mass, but as a controlled, directed force. Instead of fighting against gravity, it would command it. The Flux liner concept, explored in declassified studies and hinted at in various patents, proposes creating a localized distortion in spacetime, a kind of hill or wave that the craft would then surf along. Think of it not as a boat pushing through water with a propeller, but as a surfer gracefully riding the energy of a wave. The vehicle isn't expelling anything. It's manipulating the fabric of reality itself to create a preferred direction of travel. This principle goes far beyond even the most advanced public concepts like ion thrusters, which are still based on ejecting particles, albeit very efficiently. It's a leap from reaction-based movement to field-based movement, a shift as significant as the jump from sailboats to steam engines. So how could such an unbelievable feat even be possible? The theoretical underpinnings likely involve the precise application of incredibly high-energy electromagnetic fields. Certain patents, often filed by researchers with ties to NASA contractors, describe complex arrangements of superconductors and capacitors designed to generate spinning or oscillating fields of immense power. The idea is that these controlled energies could interact with the quantum vacuum or the gravitational field in a way that produces a net force. While this sounds like the realm of pure speculation, it's crucial to remember that we already know electromagnetic forces are astronomically stronger than gravity. A simple fridge magnet can overcome the entire gravitational pull of the Earth. The secret research may be focused on finding the precise key, the right frequency, the right configuration to unlock a gravitational effect we can control. Early experiments might have sought to measure minuscule thrusts in highly controlled laboratory settings, a far cry from a starship, but a potential first step on a revolutionary path. The implications of successfully developing such a technology are, to put it mildly, staggering. For starters, it would render the tyranny of the rocket equation obsolete. A Fluxliner-style craft would not need to carry fuel for its primary propulsion, allowing it to accelerate continuously for years, reaching speeds a significant fraction of the speed of light without the mind-boggling fuel requirements of conventional rockets. The maneuvers it could perform would defy our current understanding of aerodynamics and orbital mechanics. It could change direction instantaneously, hover motionless in the air or space without expending energy, and potentially even create its own protective field against radiation and debris. Interstellar travel, the dream of reaching other star systems within a human lifetime, would transform from a distant fantasy into a tangible engineering problem. When we contrast this with what NASA discusses publicly, the gap becomes startlingly clear. The agency proudly talks about solar sails, a wonderful technology that uses the gentle pressure of sunlight for propulsion. But compared to the potential of field propulsion, solar sails are like trying to cross an ocean on a raft with a bedsheet for a sail. It works in theory, but it's slow and leaves you utterly at the mercy of the elements. The existence of serious, albeit hidden, research into Fluxliner concepts suggests that within the highest levels of aerospace research, solar sails are seen as a modest interim solution, while the real goal is something that would make them appear primitive. This hidden work hints that a path to the stars, a true mastery of space travel, may have been discovered in theory and tested in small-scale models, a secret so profound that its acknowledgement would irrevocably alter our view of humanity's future in the cosmos. From manipulating gravity itself, we now turn to a technology that seems pulled directly from a fantasy novel, the power of invisibility. But this is not magic. It is the result of a revolutionary class of substances known as metamaterials. Picture a specially engineered surface, not unlike a microscopic jungle gym, where the precise arrangement of structures is smaller than the wavelength of light itself. This intricate architecture allows the material to interact with incoming electromagnetic waves, whether visible light, radar, or infrared heat, in ways that no natural substance ever could. Instead of simply absorbing or reflecting light, these metamaterials can be designed to guide it, coaxing photons to flow around an object like water parting around a smooth stone in a stream, seamlessly meeting again on the other side. To an observer, it would appear as if the object simply wasn't there, a perfect void in space. NASA's official public interest in such technology is perfectly logical and centers on practical spacecraft management. In the harsh environment of space, managing thermal loads and protecting sensitive instruments from radiation are constant challenges. A metamaterial coating could, for instance, be designed to perfectly reflect the intense heat of the sun on one side of a satellite while radiating internal heat away from another, acting as a super-efficient thermal cloak. It could also shield sensors from stray electromagnetic noise, allowing telescopes to peer into the cosmos with unprecedented clarity. These applications alone would be significant advancements. However, the evidence strongly suggests that classified research has ventured far beyond these passive, defensive roles into the realm of active and adaptive camouflage. This is where the technology transitions from being merely ingenious to being truly transformative. An active camouflage system wouldn't rely on a single, fixed property. Instead, it would incorporate a network of tiny sensors and actuators, creating a dynamic surface that can analyze its surrounding environment in real time and adjust its response accordingly. Imagine a material embedded with millions of microscopic cells, each one acting like a pixel on a screen. If a sensor detects the deep black of space behind it, the corresponding pixels adjust to mimic that blackness. If it moves over a cloud-strewn blue Earth, the material instantly changes to replicate the exact pattern and color, effectively projecting the background onto the foreground. This isn't just about being invisible to a single type of detection. It's about becoming undetectable across the entire electromagnetic spectrum, from the prying eyes of optical telescopes to the sophisticated sweep of radar arrays. The potential applications for such a capability are as strategic as they are breathtaking. While a stealth aircraft like the B-2 bomber is designed to have a very low radar cross-section, it is not invisible, it is merely difficult to track. A vehicle coated in an advanced active metamaterial could, in theory, reduce its signature to near zero, making it virtually undetectable to any form of long-range sensing. For NASA, this technology could be used to protect critical assets in orbit from observation or to design probes that could observe other celestial bodies without the risk of being seen themselves. But the line between civilian space exploration and national security is notoriously thin. The same technology that could hide a science probe from hypothetical extraterrestrial observers could just as easily conceal a reconnaissance satellite or an advanced aerospace platform from earthly adversaries. This brings us to a compelling and somewhat unsettling conclusion. For decades, stories of unexplained aerial phenomena, strange craft performing maneuvers that defy conventional physics, have been dismissed as fantasy. Yet, the continuous, hidden development of metamaterials for active camouflage suggests that the science behind such sightings may be more advanced than anyone outside a classified program could imagine. The shimmering, shape-shifting appearance often described by witnesses could be a side effect of an imperfect or actively adapting cloaking system, struggling to perfectly match a complex background. While this is speculative, it highlights a profound idea. The line separating the cloaking devices of science fiction from the tested capabilities in hidden laboratories may not be a thick, bold line, but a blurry, permeable boundary that we crossed years ago without even realizing it. The ability to render an object invisible, once the ultimate fantasy, may already be a carefully guarded secret of the space age. Moving from the tangible manipulation of light with metamaterials, we venture into a realm that challenges our most basic notions of reality, the quantum world. While a public-facing communication strategy is laser-focused on, lasers developing incredibly sophisticated optical systems to transmit data from deep space at unprecedented speeds, a far more radical and secure method may be undergoing secret tests. This technology doesn't rely on beaming photons across millions of miles. Instead, it harnesses one of the most bizarre and counterintuitive phenomena in all of physics: quantum entanglement. This is the mysterious connection that forms between two particles, linking their fates in such a way that whatever happens to one instantly influences the other, even if they are separated by the entire breadth of the galaxy. To wrap your mind around this, let's use that simple analogy of the magic coins. Imagine you have two special coins that are intrinsically linked. You give one to an astronaut orbiting a distant star, and you keep the other here on Earth. The moment you flip your coin and see it land on heads, you know with absolute certainty that the astronaut's coin has also landed on heads simultaneously. There is no signal traveling through space. The information is shared instantaneously. This spooky action at a distance, as Einstein famously called it, isn't just a theoretical curiosity. In laboratories around the world, scientists have repeatedly demonstrated that entangled particles, like photons or electrons, do indeed share this instantaneous connection. The monumental challenge, and the focus of what would certainly be a classified NASA program, is not proving entanglement exists, but finding a way to use it to send a deliberate, meaningful message. The primary obstacle is that you cannot simply read the state of your entangled particle to receive a message. The outcome of a measurement on one half of an entangled pair is always random. You might see heads or tails, but you can't control which one appears. So how could it possibly be used for communication? The secret lies in a technique called quantum teleportation. Without diving into the complex mathematics, the process involves using an entangled pair as a resource, combined with a traditional light-speed signal, to destroy the quantum state of a particle at one location and recreate it perfectly at the other. While the actual information still travels at the speed of light, the unique property of entanglement is what makes the transfer perfectly secure and allows for the reconstruction of the state. For a secretive probe on the far side of Mars, this would mean receiving instructions that are fundamentally impossible to intercept or jam. Any attempt to eavesdrop on the quantum channel would immediately disturb the delicate entangled state, alerting both the sender and receiver to the presence of an intruder and corrupting the message beyond recovery. This level of security is the holy grail for controlling assets where secrecy is paramount. Imagine a stealth probe investigating an anomaly in the Kuiper belt. Using quantum communication, NASA could send commands with complete confidence that no other nation or entity could listen in. But the implications reach even further than security. Consider the problem of controlling a rover on Mars in real time. With current technology, there's a communication delay of up to 20 minutes each way. You can't joystick a rover around a tricky obstacle. You have to send a batch of commands and wait to see what happens. A quantum link system, while not faster than light in the way we traditionally think, could enable a much more fluid and responsive form of control by creating an ultra-secure, high-bandwidth channel that integrates with advanced AI, effectively giving an operator on Earth a near-instantaneous connection to the machine's sensors. This isn't just about having a faster internet connection between planets. It represents a fundamental shift in the architecture of information transfer, moving from a system that broadcasts signals hoping they arrive intact to one that creates a private, unbreakable link between 2 points in space, a technology that would quietly but utterly revolutionize our ability to operate throughout the solar system. But what if the ultimate machine for exploring an alien world isn't a machine at all, at least not in the way we traditionally think? The rovers we send to Mars are marvels of engineering, but they are also fragile, rigid, and entirely dependent on commands from millions of miles away. They cannot heal from damage, they cannot adapt to unexpected terrain, and they are powered by systems that can fail in the harsh realities of space. Now envision a different kind of explorer, one born not on an assembly line, but in a laboratory where the line between robotics and biology becomes intentionally blurred. Picture a rover whose chassis is not aluminum and titanium, but a flexible, resilient polymer that mimics the structure of cartilage. Instead of electric motors, its limbs are actuated by bundles of synthetic muscle fibers, contracting and expanding with the silent strength of organic tissue. This is the frontier of biomorphic robotics and synthetic biology, a field where NASA, a most secretive research, may be creating explorers that are, in a very real sense, alive. This approach, known as biomorphism, fundamentally rethinks the problem of survival in extreme environments by looking to nature's own solutions. Here on Earth, life has already conquered every conceivable niche, from the crushing depths of the ocean trenches to the acidic, boiling hot vents of volcanoes. Organisms called extremophiles thrive in conditions that would instantly destroy any machine we currently send into space. The hidden research likely involves studying these biological champions and reverse engineering their secrets. For a mission to Europa, Jupiter's ice-covered moon with a vast subsurface ocean, a biomorphic probe might be designed like a deep-sea creature, able to navigate in total darkness using sensory systems inspired by aquatic life, and powered not by fragile solar panels but by harnessing chemical energy from the water itself, much like the organisms that live around hydrothermal vents on Earth. For the inferno-like surface of Venus, a rover might be crafted from ceramics and polymers that can withstand extreme heat and pressure, its structure capable of slight, gradual reconfiguration to navigate the rocky, volcanic landscape, much like a plant slowly growing towards the sun. The advantages of such a design philosophy are profound and extend far beyond mere durability. The most revolutionary capability would be self-repair. A traditional rover like Perseverance has a limited lifespan. If a critical component fails, the mission is severely compromised or over. A biomorphic robot, however, could be embedded with the biological equivalent of a healing factor. If its synthetic skin were torn by a sharp rock, it could secrete a polymer-based blood that hardens to seal the breach. If a synthetic muscle fiber fatigues or breaks, stem cell-like nanofactories within its body could work to regenerate the damaged tissue over time. This isn't just about redundancy. It's about creating a system that can recover from failures that would be fatal to conventional machinery, potentially extending a mission's lifespan from years to decades. Furthermore, these robots could be designed with a degree of autonomy that feels almost instinctual. Instead of waiting for hours for commands from Earth, a biomorphic explorer could possess a decentralized nervous system, allowing it to make basic decisions about navigation and obstacle avoidance based on pre-programmed biological drives, much like an insect foraging for food. This fusion of biology and machine inevitably leads us into a vast and largely unexplored ethical territory. If we create a machine that can grow, heal, and make autonomous decisions to ensure its survival, at what point does it stop being a tool and start being a form of life? Sending such a semi-living probe to another world raises profound questions about contamination. While all spacecraft are sterilized, a biomorphic robot that uses organic compounds or is capable of replication blurs the line between a sterile instrument and a potential biological agent. There are also the practical boundaries of control. How do you ensure that a self-repairing, adaptive machine doesn't evolve behaviors outside of its original programming over a long, isolated mission? The very adaptability that makes it so resilient could also make it unpredictable. The development of biomorphic robotics is not just a technical challenge, it is a philosophical one, forcing us to confront our role as creators and the responsibilities that come with designing explorers that carry the spark of life, however synthetic, to the farthest reaches of the cosmos. So far, we have navigated the manipulation of gravity, the bending of light, and the spooky connections of the quantum world. But all of these incredible technologies share a common, fundamental requirement: a vast and reliable source of power. A flux liner propulsion system or a plasma radiation shield, would demand more energy than an entire fleet of nuclear aircraft carriers could produce. This brings us to what is perhaps the ultimate prize, a technological key that would unlock all the others. We are talking about the ability to draw power from the very fabric of the universe, a concept known as zero-point energy harvesting. The idea is as radical as it sounds, suggesting that what we perceive as empty space is in fact a seething ocean of infinite energy, and that we might just have found a way to tap into it. To understand this, we must first abandon our classical view of a vacuum. We tend to think of the void between stars as a perfect, silent nothingness. But quantum physics paints a wildly different picture. At the infinitesimally small scale of the quantum realm, empty space is a turbulent foam of constant activity. Virtual particles spontaneously pop into and out of existence in a frantic dance governed by the Heisenberg uncertainty principle. This underlying frenzy means that even at a temperature of absolute zero, the point where all classical motion ceases, this quantum activity continues unabated. The energy contained in these fleeting fluctuations is known as zero-point energy, and its theoretical density is astronomical. A single cubic centimeter of pure vacuum is calculated to contain more energy than all the visible matter in the entire universe. The challenge, of course, is that this energy is locked away in a form that is incredibly difficult to access, like trying to capture the energy of 1,000,000 microscopic lightning bolts that flash and disappear in less than an instant. For decades, the mainstream scientific community has largely dismissed the practical extraction of zero-point energy as impossible, relegating it to the realm of fringe science and science fiction. The prevailing view is that it would be like trying to use the waves of the ocean to power a boat while being permanently anchored to the seabed. The energy is there, but there's no way to create a net force from it. However, this is precisely where the veil of classified research becomes so intriguing. While public science remains focused on incremental improvements in solar cell efficiency or the development of safer fission reactors, it is entirely plausible that a black budget program within NASA or its defense partners took the zero-point concept seriously. The goal of such a program would not be a small power booster, but a fundamental breakthrough, a reactor capable of creating a sustained imbalance in the quantum vacuum, effectively siphoning off a tiny, usable fraction of this background energy. The mechanism for achieving this would be as complex as the physics itself. Theoretical approaches often involve the use of rapidly oscillating electromagnetic fields or specially designed Casimir cavities devices that use incredibly close parallel plates to suppress certain quantum fluctuations, creating a measurable force between them. The secret research would aim to amplify this effect, to find a resonance or a material structure that could coherently extract energy from the vacuum's chaos. Early experiments might measure only the tiniest of effects, mere nanowatts of power, but the mere confirmation of a net energy gain would be a discovery on par with the mastery of fire or the splitting of the atom. It would prove that the vacuum is not an empty tank to be filled, but a perpetual energy source waiting to be plugged into. The implications of such a success are almost beyond comprehension. For space exploration, it would be nothing short of a revolution. A spacecraft equipped with a zero-point energy reactor would be utterly independent. It would never need to refuel. Solar panels would become obsolete for missions beyond the inner solar system, and the risks and limitations of nuclear power would vanish. A probe could operate for centuries, its power supply as constant and reliable as the universe itself, but the impact would ripple far beyond NASA missions. On Earth, this technology would resolve the global energy crisis overnight. It would provide clean, limitless, and virtually free power to every corner of the globe, rendering fossil fuels, nuclear fission, and even renewable energy farms like solar and wind obsolete. The very structure of human civilization, from economics to geopolitics, would be transformed by the abolition of energy scarcity. This is why the pursuit of zero-point energy is often called the holy grail of physics. It represents the final emancipation from the constraints that have bound humanity since its inception. The fact that such research would be conducted in the deepest secrecy is a foregone conclusion. The nation or entity that successfully harnesses the vacuum of space would attain a level of technological and economic supremacy that is absolute. The existence of a hidden program dedicated to this goal suggests that within the most secure laboratories, scientists are not just dreaming of this future. They may be actively building the engine that needs no fuel, an invention that would quietly end our age of energy dependence and inaugurate a new era for all of humanity. But what if the ultimate interface for exploring another world wasn't a screen or a joystick, but the human mind itself? We've conquered the challenge of sending sophisticated machines to distant planets, but we remain tethered to them by a fragile, sluggish thread of radio signals. The time delay, those agonizing minutes it takes for a command to travel to Mars and for a response to travel back, turns even the simplest task into a slow, plodding affair. Now let's push that boundary to its absolute limit. Imagine an astronaut not strapped into a spacecraft but seated in a control room on Earth, wearing a sleek, sensor-lined headset. They look at a live video feed from the surface of Mars, and as they simply think about reaching out to pick up a curious rock, a robotic arm millions of miles away executes the movement with the same fluid grace and intuitive precision as a human hand. This is the extraordinary promise of consciousness interface systems for telepresence, a hidden technology that seeks to merge human and machine so completely that the vast gulf of space itself seems to vanish. The core challenge of this technology is one of translation. Our brains are a symphony of electrical and chemical activity, a complex language of intent, sensation, and motor commands. A consciousness interface system must become a perfect bilingual translator for this language. It begins with an array of highly sensitive sensors, likely using a combination of electroencephalography to read the brain's electrical patterns and functional near-infrared spectroscopy to map blood flow changes, creating a high-resolution picture of neural activity. This raw data is then fed into sophisticated artificial intelligence algorithms, the true heart of the system. This eye isn't just following pre-programmed commands, it's learning the unique neural dialect of its human operator. Through extensive training, the system builds a model that correlates specific patterns of brain activity with intended actions. A faint neural spark associated with the thought of grasp is translated into the complex sequence of commands needed for a robotic hand to close around an object. The system would learn to distinguish between the intention to walk forward, turn left, or stoop down to examine the soil, all by reading the subtle preparatory signals in the brain's motor cortex before the body even twitches. The implications of achieving such a seamless link are transformative, especially when it comes to overcoming the tyranny of light-speed delay. With a traditional remote control system, an operator on Earth sees an obstacle on the Martian surface, sends a command to stop, and waits over 20 minutes to see if the rover obeyed. In that time, the rover could have already tumbled into a ravine. A consciousness interface system bypasses this delay not by making signals travel faster, which is impossible, but by placing the intelligence on site. The human operator's intent is transmitted to the robotic avatar, which then possesses a degree of sophisticated autonomy to execute the action in real time within its local environment. The AI on the rover would handle the micro-adjustments for balance and traction, while the human provides the high-level goal and the nuanced dexterity. It's the difference between giving detailed, turn-by-turn directions to a driver over a staticky phone line with a long delay, and simply being the driver yourself, reacting instantly to the road ahead. This fusion allows for a level of exploration that is both profoundly efficient and deeply intuitive, combining the lightning-fast processing and resilience of a machine with the sophisticated pattern recognition and problem-solving skills of a human being. This technology, however, pushes us beyond the realm of mere remote control into a territory that challenges our very conception of self. This isn't just virtual reality where you put on a headset and see a digital world. This is the potential for a form of telepresence so immersive that the operator begins to feel a genuine sense of embodiment within the machine. The system would need to provide sensory feedback, translating data from the rover's cameras, microphones, and tactile sensors into signals that the human brain can interpret as sight, sound, and touch. The operator might feel the gritty texture of Martian dust through the robot's fingers, or sense the strain in its actuators as it climbs a steep slope. Over time, the consciousness could so fully identify with the robotic avatar that the biological body sitting in the chair on Earth fades into the background. The human mind would, in a very real sense, be inhabiting a body on Mars, experiencing the alien landscape directly. This raises profound questions about human identity and the nature of consciousness. If your mind can live and operate through a synthetic body on another world, what defines the boundaries of yourself? Are you the fragile biological organism on Earth, or are you the resilient machine explorer on the Red Planet? The development of such a system is not just a technical milestone, it is a philosophical threshold, forcing us to consider a future where humanity can project its consciousness across the solar system, truly becoming a multi-planet species not just in body but in mind. While the concept of telepresence merges the human mind with machine intelligence, another hidden breakthrough could revolutionize the machines themselves at their most fundamental level. We are talking about the silent, invisible enemy of all advanced technology, electrical resistance. In every wire, every circuit, and every motor on a spacecraft, a portion of the precious electrical energy is lost as waste heat, a constant drain on power systems that must be meticulously managed. Now envision a world where that resistance simply vanishes. This is the promise of superconductivity, a state where electricity flows forever without any loss. The catch is that, until now, achieving this miracle has required cooling materials to temperatures colder than the void of deep space, making it impractical for most applications. But what if that monumental obstacle had already been quietly overcome in a classified laboratory? The possibility that NASA possesses a stable, room-temperature superconductor is a secret that wouldn't just improve spaceflight, it would completely redefine it. The impact of such a material on propulsion alone would be transformative. Consider the most powerful propulsion concepts we've discussed, like the Flux liner or plasma shields. These systems rely on generating immensely powerful magnetic fields, which in turn require enormous electrical currents. With conventional conductors, the energy losses from resistance would be so colossal that the systems would melt themselves into slag almost instantly. But a room-temperature superconductor changes the entire equation. It would allow for the creation of compact, incredibly powerful electromagnets that could operate indefinitely without overheating. A magnetic propulsion system that is currently just a theoretical sketch could become a practical engine, capable of generating fields strong enough to bend plasma or even manipulate spacetime with an efficiency that borders on 100%. The spacecraft's power source, whether nuclear or something more exotic, could be dedicated entirely to creating thrust, not wasted on battling the fundamental physics of its own wiring. Beyond propulsion, the implications for power management and storage are equally profound. Every spacecraft is a careful balance of energy generation and consumption, with batteries representing a critical and heavy limitation. Superconducting magnets can be used to create devices called SMES units, superconducting magnetic energy storage. These systems can store vast amounts of electrical energy almost perfectly, with charge lasting for years, and then release it in an instant if needed. For a deep space mission, this means having a compact, lightweight battery that never degrades and can provide immense bursts of power for high-energy experiments or emergency maneuvers. It effectively solves the problem of energy storage, turning a spacecraft from a vessel that must constantly recharge its batteries into one that carries a nearly perpetual, on-tap reservoir of power. Furthermore, the entire electrical grid of the spacecraft could be rewired with superconducting materials, eliminating all transmission losses. Every watt of power generated by solar panels or a reactor would go directly to where it's needed, making the vessel vastly more efficient and capable. The revolution would extend into the realm of computing as well. The heat generated by dense computer processors is a major limiting factor in how much processing power you can pack into a spacecraft's avionics. Superconducting circuits, however, produce virtually no heat. This would enable the development of supercomputers far more powerful than anything on Earth today, capable of running the complex artificial intelligence needed for autonomous navigation and real-time data analysis from a myriad of sensors. The ability to process information at such a scale would be essential for managing the sophisticated systems of an advanced spacecraft and for interpreting the torrent of scientific data collected on alien worlds. Publicly, the scientific community's pursuit of room temperature superconductivity has been a story of tantalizing near misses and stringent requirements, often involving materials that only exhibit the property under extremely high pressures, making them useless for practical applications. This public struggle, however, creates the perfect camouflage for a classified breakthrough. Behind the scenes, using methods and material science knowledge that are decades ahead of the public domain, researchers working for defense and aerospace contractors may have synthesized a stable compound or discovered a unique metamaterial structure that achieves superconductivity at ambient temperatures. The path to this discovery might have involved unconventional approaches, such as embedding rare earth elements in specific crystalline lattices or creating complex, layered structures at the nanoscale that guide electrons in a way that eliminates collisions and thus resistance. The existence of such a material would be a secret worth protecting not just for billions of dollars, but for the strategic advantage it confers across every field of technology, from energy and transportation to computing and national defense. It represents a quiet unlocking of a fundamental limit, a key that opens the door to a future where energy waste is a forgotten relic of a less advanced age. Now we pivot from the challenge of perfect communication to a technology that probes one of the most fundamental and mysterious dimensions of our universe, time itself. According to Einstein's groundbreaking theories of relativity, time is not the rigid, universal constant we experience in our daily lives. It's a flexible fabric, warped and stretched by gravity and velocity. A clock ticks slower at the base of a mountain than at its peak, and an astronaut on the International Space Station ages ever so slightly slower than their counterparts on Earth. These effects, while minuscule in our everyday world, become profound in the extreme environments of deep space. This leads us to a hidden technology that seeks not just to acknowledge these distortions, but to measure them with such exquisite precision that they become a new form of vision. We are talking about temporal sensors and chronometric anomaly detection, instruments designed to read the very wrinkles in the fabric of spacetime. Conventional space telescopes are incredible tools, but they are essentially collectors of light, radio waves, and other electromagnetic radiation. They tell us what things are made of and how they move. Chronometric sensors, however, would operate on an entirely different principle. Instead of looking at the light coming from a distant star, they would measure how that star's immense gravity affects the flow of time in its immediate vicinity. Think of it like this: if you were blindfolded, you could still map a room by listening to the echoes of a sound you make, creating a picture from acoustics. A chronometric sensor would work in a similar way, but by sending out a precise ping against the fabric of spacetime itself, and then analyzing the subtle temporal echoes that return. A massive object like a planet or a black hole would create a significant dip in spacetime, slowing time around it in a detectable pattern. By measuring these minute variations in the rate of time's passage, these sensors could create a gravitational map of unprecedented detail. The practical applications for such a capability within a secret NASA program would be immense and immediate. For navigation, a spacecraft equipped with a chronometric sensor would have an incredibly reliable way to determine its position. By comparing the local flow of time, measured by an ultra-precise atomic clock on board, with a known map of temporal distortions across the solar system, a vessel could triangulate its location with an accuracy far beyond GPS or star tracking systems. This would be especially crucial for autonomous missions in deep space, where traditional navigation signals from Earth are weak or delayed. Furthermore, these sensors could peer into the hearts of celestial bodies in a way that is currently impossible. By analyzing the specific way time is warped around a gas giant like Jupiter, scientists could deduce the density and distribution of matter deep within its swirling clouds, potentially revealing the structure of a solid core or exotic states of matter that have remained hidden from view. But the most tantalizing potential of this technology lies in its ability to hunt for the universe's most elusive theoretical phenomena. According to some solutions to Einstein's equations, structures like wormholes, hypothetical tunnels connecting distant points in spacetime, would create unique and identifiable chronometric signatures. The intense gravitational forces at a wormhole's mouth would distort time in a specific, asymmetric way that would differ from the signature of a simple black hole or a neutron star. A hidden network of these sensors, perhaps deployed on classified probes sent to the gravitational sweet spots of our solar system, could be constantly scanning the sky for these anomalous readings. Detecting such a signature would not just be a Nobel Prize-winning discovery, it would be a paradigm-shifting event, providing the first tangible evidence that interstellar travel via cosmic shortcuts might be a physical possibility. It would transform wormholes from science fiction plot devices into legitimate targets for scientific investigation. This technology fundamentally represents a new way of seeing the cosmos. For centuries, astronomy has been the study of light. Chronometry would usher in the era of studying time itself as a primary data source. The data gathered would open a window into cosmic mysteries that are completely invisible to conventional instruments. Dark matter, for instance, which reveals itself only through its gravitational pull, could be mapped directly by the way it subtly slows time in vast, empty regions of space. The sensor could potentially detect gravitational waves, ripples in spacetime with even greater sensitivity than current observatories, listening to the faint echoes of cosmic collisions from the earliest moments of the universe. This is not merely an improvement on existing tools, it is the creation of an entirely new sense for humanity, a way to perceive the hidden architecture of the universe by reading the timeless rhythm of its heartbeat. This concept pushes our imagination to its limits, moving beyond the idea of a single-purpose tool to something far more dynamic and alive. The key to this technology lies in the individual units themselves, often imagined as tiny, intelligent robots called foglets. Each foglet would be a microscopic machine, potentially no larger than a human cell, equipped with a basic computer brain, a power source, and a set of tiny manipulator arms. Think of them as robotic ants, but with the ability to link together with their neighbors to form a solid structure. By communicating with each other and executing a shared program, 1 billion of these foglets could coalesce out of a shimmering cloud to form a specific tool, like a wrench, and then, a moment later, dissolve back into the cloud only to reassemble as a delicate sensor array or a patch for a damaged hull. This is the essence of programmable matter, often poetically termed utility fog, a substance that can become almost anything you need it to be, on demand. The applications for such a technology in the isolated, high-stakes environment of space are nothing short of revolutionary. Consider the daunting challenge of building a permanent habitat on the Moon or Mars. Instead of launching prefabricated modules that are heavy, rigid, and limited in their design, a mission could deliver a canister containing what appears to be nothing more than a fine, gray dust. Once on the surface, this dust trillions of foglets would be activated. Guided by a central computer blueprint, they would swarm together, layering and interlocking to first form a foundation, then walls, internal compartments, life support systems, and even furniture. The habitat wouldn't just be built, it would grow almost organically from the ground up. And if a meteorite strike later punctured a wall, the foglets in the area could automatically detect the breach and flow to the site to repair it seamlessly, healing the structure like a biological organism healing a wound. This transforms a static, vulnerable outpost into a resilient, self-maintaining home. This adaptability extends brilliantly to the spacecraft itself. A single probe, no larger than a suitcase, could be launched with a payload of utility fog. Upon reaching its destination, say a distant asteroid, the probe's fog could reshape based on the mission's needs. It could form intricate drills and scoops to collect samples, then reconfigure into a miniature laboratory to conduct on-site analysis. If it discovered something unexpected, like a cave system, the fog could morph into a swarm of small, flying or crawling explorers to investigate. This eliminates the agonizing dilemma mission planners face today, where a spacecraft's capabilities are frozen at launch. A probe equipped with programmable matter becomes a universal tool, capable of adapting to the unknown challenges of deep space exploration without any possibility of resupply or repair from Earth. It carries a factory within itself. The development of this technology, however, hinges on staggering advancements in several fields simultaneously. Creating the foglets themselves is a monumental challenge in nanotechnology, requiring them to be strong, energy efficient, and capable of complex computation at a microscopic scale. Powering such a swarm is another huge hurdle. They might draw energy from ambient light, temperature differences, or even broadcast power from a central source. But perhaps the most complex problem is the software, the hive mind intelligence that coordinates the actions of countless individual units to create a coherent, functional whole. This requires algorithms of immense sophistication to prevent chaos and ensure the assembled structure has the precise physical properties, rigidity, flexibility, conductivity required for the task at hand. The fact that classified research is likely pursuing this suggests that breakthroughs in distributed computing and nanoscale engineering may be far more advanced than what we see in the public sector. This isn't just about building better robots, it's about mastering the art of guided, intelligent self-assembly, a capability that would quietly redefine the relationship between a mission's design and the unpredictable reality of deep space. After exploring the mind-bending possibilities of programmable matter, we arrive at a concept that represents perhaps the ultimate ambition in physics: the direct control of gravity itself. The idea of defying Earth's pull has captivated humanity for centuries, from ancient myths to modern science fiction. But what if the research has moved beyond fantasy into the realm of clandestine experimentation? While NASA public research is heavily focused on understanding and working within the constraints of microgravity, its most advanced physics groups may have been pursuing a far more radical goal. The focus of these hidden investigations likely centers on a fascinating principle: using high-frequency fields to interact with and potentially counteract the gravitational force. This approach is fundamentally different from anything in conventional aerospace. An airplane generates lift by pushing air down. A rocket achieves thrust by expelling mass at high velocity. Both are methods of overpowering gravity through brute force. The experiments we're considering here operate on an entirely different principle. They wouldn't create lift in the traditional sense. Instead, the goal would be to alter the properties of spacetime within a very specific, localized area. The theoretical basis suggests that by subjecting a region to intensely powerful and rapidly oscillating electromagnetic fields, or perhaps even precise acoustic vibrations, researchers could create a kind of bubble where the influence of gravity is subtly modified. Imagine the gravitational field not as a constant, unwavering force, but as a fabric that can be made to vibrate at a specific resonance. If you can match that resonance with an external field, you might cause the fabric to ripple in a way that reduces its pull on an object placed within that zone. The mechanisms for such an effect are deeply rooted in speculative but serious physics. One avenue of exploration might involve the coupling between electromagnetism and gravity, two of the fundamental forces of nature. While they are phenomenally different in strength, theories like Kaluza-Klein or certain interpretations of quantum gravity suggest they may be interconnected at a deeper level. An experiment might use a sophisticated device, perhaps a spinning superconductor cooled to extreme temperatures and charged with a high-voltage, high-frequency current. The idea would be that the intense, controlled energy of the electromagnetic field could, under the right conditions, produce a minute gravitational effect, a slight pushing or pulling force that is unrelated to mass. Another approach could explore sonoluminescence, the phenomenon where sound waves in a liquid create tiny, collapsing bubbles that emit flashes of light. The forces involved in that collapse are immense, and some researchers have hypothesized that such focused acoustic energy could produce measurable spacetime distortions. The goal of a classified program would be to scale these subtle, often debated laboratory effects into something significant and controllable. If such experiments were even partially successful, the implications would be nothing short of earth-shattering, reshaping entire industries and our understanding of the universe. For propulsion, the most obvious application, the benefits are clear. A vehicle equipped with a gravity-modifying device would not need wings, propellers, or rocket fuel to stay aloft. It could simply reduce its effective weight, or even make it negative, allowing for silent, effortless lift and movement in any direction. The energy required, while still substantial, would be dedicated to powering the field generators rather than fighting drag and gravity through mechanical means. This would enable craft of seemingly impossible maneuverability, capable of hovering motionlessly, accelerating instantaneously, and making sharp, 90-degree turns without subjecting any occupants to crushing G-forces, as the inertia of the craft itself would be manipulated. The impact would extend far beyond flying cars or advanced aircraft. In the realm of construction, the ability to negate gravity, even temporarily, would revolutionize how we build. Massive structures, from skyscrapers to space station components, could be assembled with ease. Heavy components would weigh nothing when active field generators were applied, allowing them to be positioned with pinpoint accuracy by a single worker. This would drastically reduce the need for cranes, scaffolding, and other heavy machinery, making construction faster, safer, and far less expensive. In manufacturing, the handling of delicate but heavy materials, like large glass panels or exotic metal alloys, would become trivial. The technology could also lead to new forms of energy generation. If you can create a sustained gravitational differential, you could, in theory, build a generator that harnesses that potential energy, much like a hydroelectric dam uses water, but in a closed, perpetual system. Perhaps the most profound implication, however, is what success would mean for fundamental physics. Proving that gravity can be manipulated in a lab would force a complete rewrite of Einstein's theory of general relativity. It would demonstrate that gravity is not just a passive curvature of spacetime caused by mass, but an active field that can be engineered and shaped, much like we engineer magnetic fields today. This would bridge the gap between gravity and the other fundamental forces, providing the first real clue toward the long-sought theory of everything. The very fact that such research would be conducted in the deepest secrecy is a testament to its disruptive potential. A nation that held the key to controlling gravity would hold an advantage so comprehensive militarily, economically, and scientifically that its power would be virtually unassailable. The quiet pursuit of this ultimate prize suggests that our potential to command the physical environment may be far greater than the public equations of physics would ever lead us to believe. While the concept of manipulating gravity with high-frequency fields pushes the boundaries of known physics, it still operates within the familiar framework of positive energy and mass. But what if the key to unlocking the universe's ultimate shortcuts requires us to venture into a far more bizarre and counterintuitive territory, a realm where matter itself possesses properties that seem to defy logic? This brings us to one of the most speculative yet potentially groundbreaking hidden technologies, the synthesis of exotic matter. To understand why this is so crucial, we need to revisit one of the most thrilling ideas in theoretical physics, the Alcubierre warp drive. This concept, proposed by physicist Miguel Alcubierre in the 1990s, offers a mathematically sound method for faster-than-light travel without violating Einstein's prohibition on moving through space faster than light. Instead, the drive would work by creating a bubble of flat spacetime around a spacecraft, while contracting the space in front of it and expanding the space behind it. In essence, the ship would remain stationary within this bubble while the fabric of the universe itself moves around it, like a surfer riding a wave. It's an elegant solution to a cosmic speed limit, but it comes with one monumental catch. Fueling this incredible feat requires a type of material that, as far as public science is concerned, doesn't exist. This material is exotic matter. Exotic matter isn't just rare or strange, it's theorized to have a property that turns physics on its head: negative energy density. Imagine a substance that, instead of being attracted by gravity, is repelled by it. If you had a block of this material, it would fall upwards. This negative energy, or negative mass, is the essential ingredient for the Alcubierre drive because it's what would generate the repulsive gravity needed to inflate the spacetime behind the ship and the attractive gravity to contract the spacetime in front. Without it, the entire concept remains a beautiful but impossible daydream. Publicly, the scientific consensus is that while the equations allow for such matter, it is likely impossible to create or stabilize in the real world. relegating the warp drive to the pages of science fiction. However, this public dismissal creates the perfect veil for a highly classified, high-risk research program deep within NASA, and most secure partnerships. The goal of such a program would not be to construct a full-scale warp engine in a secret hangar, but to achieve something far more fundamental: the laboratory creation and stabilization of even a microscopic amount of exotic matter. So, how would one go about creating something that, by its very definition, seems unnatural? The most likely avenues involve harnessing the bizarre rules of quantum mechanics. One promising approach centers on the Casimir effect, a well-documented phenomenon where two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum experience a slight attractive force. This happens because the space between the plates restricts the types of quantum fluctuations that can occur, resulting in lower energy density between the plates than in the surrounding space. In a sense, the region between the plates exhibits a tiny, temporary negative energy density relative to the vacuum outside. A secret research program would be focused on amplifying this effect, perhaps by using metamaterials with intricate nanostructures to manipulate the quantum vacuum with far greater precision. Another avenue could involve high-energy particle collisions, using a device like a specialized particle accelerator to try to create exotic particles that decay almost instantly. The challenge would be to find a way to capture and sustain these fleeting entities, to somehow freeze them in a stable state for even a fraction of a second longer than nature normally allows. The significance of such an achievement, however small, cannot be overstated. Successfully creating a stable speck of exotic matter, perhaps no larger than a few atoms, would be an event on par with the first controlled nuclear chain reaction. It would do more than just prove a theory. It would validate an entire new frontier of physics. The mere existence of a demonstrable sample would shift exotic matter from a mathematical curiosity into a legitimate field of engineering. It would provide the first tangible evidence that the physics underpinning faster-than-light travel are not just equations on a chalkboard, but actual laws of nature that can be manipulated and harnessed. This single discovery would open a credible, tangible path toward the stars, transforming humanity's future from one confined to our solar system to one that encompasses the galaxy. The secret possession of such a capability would be the most profound in human history, a quiet realization that the universe is far more malleable and far more accessible than we have ever been allowed to believe. From the tangible manipulation of exotic matter, we now journey into what is arguably the most speculative and controversial territory on our list, a domain where the solid ground of classical physics gives way to the misty frontiers of consciousness itself. This is the realm of psychotronic influence and non-local effects, a field that investigates the tantalizing possibility that the human mind can interact with the physical world in ways that defy conventional explanation. Imagine an astronaut isolated in the profound silence of deep space, using focused intention to calibrate a sensitive instrument or to influence the outcome of a random number generator aboard their spacecraft. This concept, often termed psychotronics, moves beyond the brain-machine interfaces we discussed earlier. It suggests a direct, non-physical connection between consciousness and matter, a connection that operates outside the bounds of known energy or force. The idea that human intention could affect physical systems is not a new one, but its investigation within a scientific, albeit classified, framework has a documented history, particularly within military and intelligence circles. During the Cold War, both the United States and the Soviet Union poured significant resources into researching phenomena like remote viewing, the ability to perceive distant locations or events without the use of the ordinary senses. Declassified documents from projects like Stargate reveal a serious, sustained effort to determine if such skills could be harnessed for espionage. The logical extension of this research, and the part most relevant to a space agency like NASA, would be its application in the unique environment of space. The extreme isolation, high stress, and altered states of consciousness that can occur during long-duration missions create a perfect laboratory for testing whether a crew's collective mental state could have a measurable impact on the spacecraft systems or the success of critical operations. What might these experiments have looked like in practice? They likely fell into two broad categories. The first would involve attempts to improve technological reliability through mental focus. This could mean having highly trained meditators or individuals deemed to have strong psychokinetic abilities attempt to influence the behavior of sensitive electronic components, perhaps trying to reduce error rates in a computer's memory or stabilize the output of a fingy power supply. The underlying hypothesis would be that consciousness could introduce a subtle ordering influence on seemingly random quantum-level events, bringing a degree of harmony to systems prone to chaos. The second category would be more exploratory, focusing on perception beyond the physical senses. This is where remote viewing experiments would come into play, potentially used not for spying on earthly targets, but for gathering data about celestial phenomena or even scouting potential landing sites on distant planets through means that bypass light speed delay entirely. The goal would be to see if human consciousness could act as a form of non-local sensor, tapping into information not constrained by space or time. It is crucial to acknowledge that this field exists on the very fringes of science, and mainstream physics currently has no mechanism to explain how such effects could operate. The prevailing materialistic view holds that the mind is a product of the brain, and consciousness cannot exist independently to affect the outside world without a physical intermediary. However, the persistent interest from defense and intelligence agencies suggests that, despite the lack of an accepted theory, anomalous results may have been observed that were significant enough to warrant continued, if secret, investigation. For an agency like NASA, the potential payoff would be immense. If a crew's positive mental state could genuinely enhance the reliability of their vessel, or if a form of non-local intuition could provide navigational or scientific insights unavailable to conventional instruments, it would represent a revolutionary asset for deep space exploration, turning the human mind into the most advanced and adaptable tool on the spacecraft. This frontier ultimately forces us to confront the very definition of science and the boundaries of what we consider possible. The study of psychotronics challenges the core assumption that reality is purely objective and independent of the observer. If consciousness can indeed influence physical systems, then the observer becomes a participant in a fundamental way, and our entire scientific methodology may need to expand to accommodate subjective experience as a valid variable. The decision to research such phenomena in secret is understandable. The potential for ridicule is high, and any positive results would be so paradigm-shattering that they would require an extraordinary burden of proof before being revealed to the world. Whether these investigations yielded concrete results or were ultimately shelved as inconclusive, their very existence within classified programs hints at a willingness to explore the deepest mysteries of the human mind, venturing into a space where the line between the observer and the cosmos they seek to explore may be far thinner than we have ever dared to imagine. Now we arrive at a concept that represents the ultimate expression of humanity's desire to explore, a technology so powerful and so autonomous that it could potentially fill the entire galaxy with our presence without us ever needing to leave our home world. This is the idea of the self-replicating von Neumann probe, named after the brilliant mathematician John von Neumann, who first seriously explored the logic of machines capable of copying themselves. Imagine a single, sophisticated probe launched from Earth towards a nearby star system like Alpha Centauri. After a journey of decades or even centuries, it arrives not as a passive observer, but as an active industrialist. Its first task is to seek out raw materials, perhaps by landing on a mineral-rich asteroid or a moon without an atmosphere. Then, using advanced nanotechnology, it would begin to disassemble the very ground beneath it, atom by atom, using these raw materials to construct an exact duplicate of itself. Once the copy is complete and activated, the original probe and its clone would then launch themselves towards two new star systems, where the process would begin again. In a relatively short period of time, cosmically speaking, a single seed could blossom into a network of millions of probes, systematically exploring every corner of the Milky Way. The technological symphony required to make this a reality is almost beyond comprehension, integrating three of the most advanced fields we've discussed. First, it demands robotics of an unimaginable sophistication. We are not talking about the robotic arm on a Mars rover. This probe would need to be a universal factory, equipped with manipulators capable of both fine, delicate assembly and heavy-duty mining operations. Second, it requires a level of artificial intelligence that borders on true consciousness. The probe's AI would need to be a master problem solver, able to assess a completely alien environment, identify usable resources, diagnose and repair any malfunctions in its own complex systems, and make critical decisions without any possibility of guidance from Earth. It would need to be resilient, adaptable, and utterly self-reliant. Finally, the entire process hinges on nanotechnology, the ability to manipulate matter at the atomic scale. This is the key to the replication magic. The probe would essentially carry a digital blueprint of itself and use swarms of molecular assemblers to transform piles of asteroid rock into structured metals, advanced processors, and delicate sensors, building a perfect copy from the ground up. While this sounds like the plot of a science fiction novel, it is a near certainty that hidden design studies within NASA and its partner organizations like DARPA have produced detailed blueprints for such a machine. These would not be casual thought experiments, but serious engineering analyses examining the feasibility of every subsystem, from the power source needed to run a mobile factory, likely a compact nuclear reactor, to the communication system that would allow the growing network of probes to share its discoveries back to awaiting humanity. The primary motivation for keeping such studies secret is not merely the competitive advantage in exploration, but the staggering ethical and existential risks involved. The most famous of these is the dreaded gray goo scenario. What if a probe's replication instructions become corrupted? Instead of building a new explorer, it might continue replicating endlessly, consuming entire planets, moons, and eventually star systems, converting all matter into a swarm of malfunctioning probes, effectively erasing the cosmic ecology. Even without a malfunction, the very act of a von Neumann probe mining an asteroid belt could be seen as an act of cosmic vandalism by any other intelligence that might exist, potentially triggering an interstellar conflict over resources we didn't even know were claimed. This leads to the most profound implication of all. If such a technology is feasible for us, then it has almost certainly been feasible for any civilization that arose a few thousand or million years before us. The fact that we do not see clear evidence of such probes in our own solar system, no alien factories on Mars or mining operations in the asteroid belt, poses a haunting question known as the Fermi paradox. Where is everybody? The absence of von Neumann probes could be a terrifying sign. It might suggest that the Great Filter, a hypothetical barrier that prevents life from advancing to a galactic scale, lies ahead of us. Perhaps every civilization that ever develops self-replicating technology inevitably succumbs to it, either through accidental self-destruction or a conscious decision that the risks are simply too great to ever launch the first probe. The intense secrecy surrounding this research, therefore, is not just about protecting a technological breakthrough. It is about grappling with a potential cosmic verdict on the fate of intelligent life. The decision to build or not to build a von Neumann probe may be the most significant choice humanity ever makes, a choice between becoming a galactic species and unleashing a potential plague upon the stars. The ambition to not just visit other worlds but to truly live on them represents the grandest scale of human engineering imaginable. We've sent rovers to Mars and telescopes to peer at distant exoplanets, but these are acts of observation. The next logical and indeed necessary step is transformation. This brings us to a hidden technology that shifts NASA, a mission from one of exploration to one of cosmic landscaping, atmospheric condensation and terraforming. This is not about building a single habitat or a small greenhouse on Mars. It is about re-engineering an entire planet, turning a cold, barren, and radiation-scoured world into a second home for humanity. The very concept sounds like the plot of an epic science fiction saga, but classified research within NASA almost certainly contains detailed, serious plans for how to accomplish this over centuries. The primary target for such an endeavor is, of course, Mars. The red planet presents a formidable challenge. Its atmosphere is tragically thin, about 1% of Earth's, offering little protection from solar radiation and unable to trap heat, resulting in average temperatures of 80 degrees below 0 Fahrenheit. The first and most critical phase of any terraforming plan would focus on triggering a runaway greenhouse effect to thicken the atmosphere and warm the planet. Public scientific papers have discussed ideas like redirecting comets rich in ammonia, a potent greenhouse gas, to impact the Martian poles or releasing chlorofluorocarbons from manufactured factories on the surface. However, a classified program would explore far more efficient and controlled methods. One hidden technology might involve the use of focused orbital energy beams, perhaps from gigantic solar power satellites, to precisely vaporize the vast reserves of frozen carbon dioxide known to exist at the Martian poles. By sublimating these ice caps, enormous quantities of CO2 would be pumped into the atmosphere, kick-starting the warming process. This would be a delicate operation, requiring technology to manage the release in a controlled manner to avoid chaotic climate shifts, but it represents a direct and powerful lever to pull on a planetary scale. Once a thicker, warmer atmosphere is established, the next monumental task would be to transform its composition. A CO2-rich atmosphere is a start, but humans need oxygen to breathe. This is where biological technologies, likely developed in the utmost secrecy, would come into play. The most elegant solution would be to seed the Martian landscape with genetically engineered microorganisms. Scientists could design extremophile bacteria or algae, tailored to thrive in the harsh Martian soil and the new, denser atmosphere. These microbes would be programmed with a single, vital purpose: to consume carbon dioxide and release oxygen through photosynthesis. This is essentially the same process that transformed Earth's own atmosphere billions of years ago, but here it would be guided and accelerated by human design. These organisms would need to be incredibly resilient, capable of surviving intense ultraviolet radiation until a protective ozone layer could form, and able to reproduce rapidly to cover vast areas of the planet. The research into creating such supermicrobes would be a fusion of synthetic biology, astrobiology, and environmental science. representing a level of control over life itself that is currently unimaginable. Beyond atmospheric engineering, a hidden terraforming program would also include plans for large-scale physical interventions to make the environment more Earth-like. One of the most breathtaking concepts is the deployment of orbital mirrors. These would not be simple pieces of polished metal, but vast, ultra-thin, and likely adaptive structures, miles across, placed in a special orbit to reflect sunlight onto specific regions of Mars, such as the polar caps, to further accelerate melting and warming. Another radical idea might involve creating an artificial magnetic field. Mars lacks a global magnetic field like Earth's, which is a primary reason its atmosphere was stripped away by the solar wind over billions of years. A classified study might propose launching a powerful electromagnetic satellite to a stable point between Mars and the Sun, generating a protective magnetic bubble that would shield the newly thickened atmosphere from erosion, ensuring the work of centuries is not undone. This would be an undertaking of staggering proportions, requiring power sources we can barely conceive of today, but it highlights the kind of long-term, systems-level thinking that would define a true terraforming initiative. The very existence of such research, however, is kept quiet for reasons that go far beyond technical challenges. The ethical and philosophical debates surrounding terraforming are immense and fraught with complexity. The most significant question is one of planetary protection. What if Mars, beneath its barren surface, hosts its own simple microbial life? By embarking on a project to change the entire planet, would we be committing an act of interplanetary genocide, wiping out the only other known life in the universe? Even if Mars is completely sterile, do we have the right to completely reshape another world, to overwrite its billions of years of geological history according to our own needs and desires? It is an act of playing God on a literally planetary scale. Publicly engaging in this debate prematurely could trigger widespread opposition and stifle the research before it even begins. By keeping these plans confidential, NASA can allow the foundational science and technology to advance without being hampered by a potentially contentious and divisive public discourse. Furthermore, acknowledging such multi-century plans would fundamentally alter humanity's perception of its own future and NASA's role in it. It signals a commitment to a project that would span dozens of generations, a level of long-term planning that our species has rarely demonstrated. It transforms the space agency from an organization focused on exploration and discovery into one tasked with nothing less than the creation of a new branch of human civilization. This is an ambition of such profound scope that its admission would reshape global politics, economics, and culture. The quiet pursuit of terraforming technologies, therefore, is not merely about hiding blueprints. It is about managing the societal shockwave that would accompany the realization that we are no longer just visitors to the solar system, but are actively beginning the process of moving in. As we venture further into the cosmos, the sheer volume of information we collect becomes both our greatest treasure and our most daunting challenge. Every high-resolution image from a distant moon, every spectral analysis of an exoplanet's atmosphere, every byte of sensor data from a deep space probe represents a priceless piece of the cosmic puzzle. But this deluge of data creates a monumental problem. How do we store it all reliably for the decades or even centuries that a mission may last? Publicly, our answer has been to rely on increasingly advanced solid-state drives, the same basic technology found in a modern laptop, albeit radiation-hardened. These are remarkable devices, but they have inherent limitations. They are susceptible to cosmic radiation, which can flip bits and corrupt files over time, and they have a finite lifespan. For a mission intended to last 10,000 years, like a probe destined for another star, our current storage methods are as ephemeral as a sandcastle against the tide. This is where a hidden technology, one that seems to borrow from the lore of ancient crystals and futuristic science, offers a revolutionary solution: holographic data storage and memory crystals. The fundamental breakthrough of this approach lies in moving from 2 dimensions to 3. A conventional hard drive or solid-state memory stores data on a surface, like writing on a single sheet of paper. You can only fit so many words on that page. Holographic storage, however, uses the entire volume of a material, like writing on thousands of transparent sheets stacked together, and being able to read every word on every sheet without disturbing the others. This is achieved by using lasers. To store data, a signal laser beam encoded with a digital pattern is crossed with a reference laser beam inside a special light-sensitive crystal. Where these beams interfere with each other, they create a unique 3-dimensional pattern, a hologram, that is permanently etched into the crystal's atomic structure. This isn't a simple image, it's a complex interference pattern that can represent a massive amount of digital information. To retrieve the data, you simply shine the reference laser back through the crystal, which reconstructs the original signal beam and its encoded data. This method allows for staggering data densities. A crystal no larger than a sugar cube could, in theory, hold multiple terabytes of information, the equivalent of entire national libraries encoded in a speck of matter you could hold between your fingers. The advantages for space exploration are immediately obvious and go far beyond mere capacity. The first is unparalleled durability. These memory crystals are not based on delicate electronic circuits. They are a permanent physical change in the structure of the crystal itself, much like a fossil is a permanent record in stone. This makes them incredibly resilient to the hazards of space. Cosmic rays and other forms of radiation that would slowly degrade and destroy conventional electronic memory have a negligible effect on the stable atomic lattice of a crystal. The data is safe from the constant bombardment that plagues long-duration missions. Furthermore, these crystals are immune to the effects of extreme temperatures, vacuum, and time. They require no power to maintain the data. Once written, the information is locked in place, waiting patiently for millions of years to be read. This transforms data storage from an active, power-hungry process into a passive, permanent recording, a critical consideration for a probe that must operate autonomously for generations. This leads to the most profound application of this hidden technology, the creation of immortal libraries. Imagine a probe like Voyager carrying its golden record with greetings from Earth, but instead of a few images and sounds, it carries a crystal containing the entirety of human knowledge, our history, our science, our art, every book ever written, every significant discovery. This isn't just a message in a bottle. It's a time capsule designed to survive not just thousands, but potentially millions of years. For a civilization that might find it long after our sun has died, such a crystal would be an indestructible record of a species that once looked to the stars. But the purpose isn't solely for aliens. This technology is the perfect solution for humanity's own long-term archives. As we establish a permanent presence on the Moon and Mars, we will want to create backups of our most vital information, repositories that can survive any catastrophe on Earth. A library of memory crystals buried in a stable lunar lava tube could preserve the collective knowledge of our species safe from war, natural disaster, or planetary collapse, ensuring that our story is never truly lost. The implications for active missions are equally transformative. A deep space telescope freed from the constraints of data storage could operate in a completely new way. Instead of carefully selecting which images to send back to Earth due to bandwidth limitations, It could capture continuous, ultra-high-resolution video of a planetary system for years, storing petabytes of data in a small, robust crystal bank. When the mission is complete, or when a faster data retrieval method becomes available, this entire treasure trove of observation could be transmitted home, providing a complete and uninterrupted record of cosmic events. This turns a snapshot mission into a long-term observatory, capturing dynamic processes like atmospheric weather on distant gas giants or the slow dance of asteroid collisions in unprecedented detail. The crystal becomes more than a storage device. It is a silent, patient witness to the universe, capturing light that has traveled for eons and preserving it for future generations to study. This hidden advancement, therefore, is not just an incremental improvement in memory technology. It is the key to creating a permanent, incorruptible memory for our species, a way to ensure that our discoveries in the void of space are not fleeting glimpses, but enduring legacies carved in stone for the ages. While the vacuum of space may seem empty, it is in fact a torrential river of deadly energy, a silent storm of radiation that represents one of the single greatest threats to human exploration beyond the protective bubble of Earth's magnetic field. This invisible onslaught comes in two primary forms: the predictable but intense bursts from our own sun during solar flares, and the far more penetrating cosmic rays, which are high-energy atomic nuclei screaming across the galaxy at nearly the speed of light. When these particles slam into the human body, they can shred DNA, increase cancer risks, and even cause cognitive damage over time, posing a mission-ending danger for a crew traveling to Mars or establishing a base on the Moon. Publicly discussed solutions to this problem have a distinctly low-tech feel, reflecting the immense difficulty of the challenge. Proposals often involve using the spacecraft's own water supply as a shielding layer, literally surrounding the crew quarters with tanks of water, or building habitats out of Martian regolith, essentially burying astronauts underground to protect them. Other concepts explore recreating a miniature version of Earth's magnetic field around the vessel, using superconductors to generate a protective magnetosphere. But while these ideas have merit, they are also incredibly heavy, energy-intensive, or logistically complex. A far more elegant and advanced solution, likely developed in secret, takes its inspiration from the most powerful natural shields in the universe, the stars themselves. This is the concept of the electromagnetic plasma shield. To understand how this would work, we first need to grasp what plasma is. Often called the fourth state of matter, plasma is an ionized gas, a superheated soup of atoms that have been stripped of their electrons, creating a sea of charged particles. Every star, including our Sun, is a massive ball of plasma. The key property of plasma for our purposes is that it is exquisitely responsive to magnetic fields. You can contain it, shape it, and manipulate it with magnetism. Now, imagine a spacecraft equipped with a series of compact but powerful electromagnetic coils. When activated, these coils would not create a simple magnetic bubble. Instead, they would be used to generate and then confine a thin layer of plasma around the entire hull of the vessel. This wouldn't be the scorching, million-degree plasma of a star's core. It would be a much cooler, controlled, and magnetically suspended layer. From the outside, it might appear as a faint, shimmering aura surrounding the ship, a visible force field dancing with ethereal light. This glowing envelope is the shield. The protective magic happens through the fundamental physics of charged particle interaction. The deadly radiation in space, protons from the sun, and atomic nuclei from cosmic rays are all electrically charged. As these particles approach the plasma shield, they encounter a barrier that is itself composed of charged particles. The incoming radiation is repelled by the similar charges within the plasma, its path bent and deflected away from the spacecraft, much like a magnet pushing against another magnet of the same pole. This active deflection is infinitely more effective than passive shielding, which relies on simply having enough mass, like water or metal, to absorb the radiation through countless atomic collisions. Passive shielding can actually make the problem worse in some cases, as high-energy particles striking dense materials can create a secondary shower of even more radiation. A plasma shield, by contrast, creates a clean, energetic barrier that turns the harmful particles away before they ever reach the hull, leaving the spacecraft and its crew untouched inside a safe, quiet bubble. The advantages of such a system are profound. Unlike a water shield which gets consumed or a lead shield that adds crippling weight, a plasma shield is massless. Once the system is activated, the shield itself weighs nothing, a critical consideration for the rocket equation where every kilogram launched into space carries an exponential cost. Furthermore, it is dynamically reconfigurable. The strength and density of the plasma layer could be adjusted in real time based on the radiation environment. During a predictable solar event, the shield could be powered up to maximum intensity and then dialed back down to a maintenance level during quieter periods, optimizing energy use. It could also be shaped, perhaps strengthened at the bow of the ship, the direction of travel, to better handle the impact of particles. This adaptability makes it the perfect technology for long-duration missions where the crew cannot simply turn back if radiation levels spike. This incredible capability, however, hinges on one monumental requirement: power. Generating and sustaining a stable, ship-sized envelope of magnetically confined plasma would demand an immense and continuous supply of electrical energy, far beyond what solar panels or even current-generation nuclear reactors could provide for a manned spacecraft. The very plausibility of a hidden plasma shield program, therefore, is inextricably linked to the breakthroughs we discussed earlier, particularly in room temperature superconductors and zero-point energy harvesting. A compact, high-output power source, possibly drawing energy from the quantum vacuum itself, would be the essential engine needed to make the plasma shield a practical reality. This interconnection reveals a compelling pattern within the hidden technology landscape. The solutions to the biggest challenges of spaceflight are not isolated inventions, but parts of an integrated technological tapestry. The development of a radical new propulsion system necessitates a revolutionary power source, which in turn enables a transformative life support technology like the plasma shield. Each secret breakthrough doesn't just solve one problem, it unlocks the potential for several others, painting a picture of a coordinated, long-term strategy to overcome every fundamental barrier to humanity's future among the stars. The existence of research into plasma shields suggests that the problem of deep space radiation may not be the dead end it publicly appears to be, but rather a challenge that has already been met with a solution as beautiful as it is powerful. The concept of physically touching anything in space is fraught with hidden dangers. A robotic arm, no matter how advanced, relies on a firm grip. But what if that grip is too firm, crushing a delicate crystalline sample from a comet? Or what if the target is tumbling unpredictably, making a safe grapple impossible? In the high-stakes, zero-friction environment beyond our atmosphere, the gentlest nudge can send an object spinning irretrievably into the void. This fundamental problem of contact has likely led NASA, hidden research teams, to explore a far more elegant solution, one that seems to defy intuition, using the invisible force of sound itself to reach out and touch the untouchable. This is the world of acoustic levitation and tractor beams, a technology that turns the silent vacuum of space into a capable and precise pair of hands. At its core, the principle is surprisingly straightforward, rooted in the physics of sound waves. Sound is not just something we hear, it is a physical pressure wave traveling through a medium, whether that's air, water, or even a solid. When these waves intersect, they create patterns of high and low pressure. Acoustic levitation works by generating standing waves that appear to be stationary, using an array of precisely calibrated speakers or transducers. At the points where the peaks of these waves meet, they create tiny, stable zones of high pressure. Conversely, where the troughs meet, areas of low pressure form. By carefully controlling the sound field, researchers can essentially create an invisible, three-dimensional energy landscape. A small object, like a droplet of liquid or a fragile component, can be trapped within one of these high-pressure points, suspended in mid-air as if by magic, held in place by the constant, gentle push of the sound waves from all sides. It's like balancing a ping-pong ball on the jet of air from a hairdryer, but with infinitely more control and stability. Now, take this concept from a laboratory on Earth and project it into the unique environment of space. While space itself is a vacuum and cannot carry sound, a spacecraft or space station is filled with air. NASA classified microgravity research would have seen the immense value of this for handling highly sensitive materials. Imagine a module on a space station dedicated to manufacturing perfect pharmaceutical crystals or ultra-pure metal alloys, processes that are ruined by the slightest contact with a container wall. With acoustic levitation, these materials could be mixed, heated, and cooled while floating completely contact-free within a carefully orchestrated sound field. This isn't just a convenience. It's the key to producing substances with perfect molecular structures, materials with properties impossible to achieve under the influence of gravity or container-induced impurities. The technology provides a level of cleanliness and control that transforms an orbiting laboratory into a factory for the next generation of miracles. But the truly revolutionary application lies in scaling this principle up and turning it outward, beyond the pressurized confines of a spacecraft. This is where the science fiction dream of the tractor beam becomes a tangible engineering goal. A tractor beam would not use sound waves directly, as there's no air in space to carry them. Instead, it would likely employ a related principle using electromagnetic waves, such as lasers. The idea is to create a similar push-pull effect with light. By using specially shaped laser beams, known as Bessel beams or optical vortices, it's theoretically possible to create a region where the light's energy patterns can exert force on microscopic particles. The laser light itself exerts radiation pressure, a tiny but measurable force. More cleverly, by manipulating the phase and intensity of the light within the beam, engineers could create a gradient that pulls a small object back toward the source. It's a far more complex feat than acoustic levitation, but the underlying concept is analogous, using waves of energy to create a controlled force at a distance. The practical uses for such a capability in orbit are immediate and incredibly valuable. Consider the growing problem of space debris, thousands of defunct satellites and fragments whizzing around Earth at lethal speeds. Sending a robotic spacecraft to capture a tumbling, jagged piece of debris with a mechanical arm is an extraordinarily risky maneuver. A single miscalculation could result in a catastrophic collision. A tractor beam, however, offers a graceful and safe alternative. A dedicated salvage satellite could approach a piece of debris and, from a safe distance of several meters, use its tractor beam to first stabilize the object's tumble, then gently draw it in for secure attachment. This same technology would be indispensable for satellite servicing. A robotic repair vehicle could rendezvous with a malfunctioning communications satellite, capture a replacement component launched from Earth with its tractor beam, and guide it into place for installation, all without a single physical clamp or risky grapple. It transforms complex, dangerous mechanical operations into clean, remote-controlled procedures. Furthermore, this technology would revolutionize the collection of samples from otherwise inaccessible locations. A probe visiting a comet or a fragile asteroid could use a tractor beam to pluck pristine dust particles directly from the object's surface or its surrounding coma without the risk of landing and potentially contaminating or damaging the terrain. It could even be used to capture and analyze the thin wisps of atmosphere from a distant moon like Titan, all while the main spacecraft remains in a stable orbit. This ability to reach out and gently touch the cosmos from a safe distance represents a fundamental shift in how we interact with the solar system. It moves us away from the brute force methodology of landing and drilling towards a more nuanced surgical approach to exploration. The development of acoustic levitation and its cosmic cousin, the tractor beam, demonstrates a hidden pursuit of finesse over force, a quiet acknowledgement that the future of space exploration may depend not on stronger grips, but on more subtle and intelligent ways of applying touch without any contact at all. For all the incredible technologies we have explored, from cloaking devices to warp drives, one of the most fundamental challenges of long-term spaceflight remains deceptively simple: the need for a steady, downward pull. Our bodies, after all, are exquisitely adapted to a lifetime spent in Earth's one-gravity environment. Remove that constant force, and the human system begins to unravel in subtle and profound ways. Astronauts on the International Space Station experience muscle atrophy, bone density loss, and even changes in their vision as fluids shift upward toward their heads in the persistent state of freefall. The most well-known solution to this problem is as elegant as it is ancient: spin. If you rotate a spacecraft, centrifugal force will push objects and people outward against the interior hull, creating a sensation that feels remarkably like gravity. This is the principle behind the iconic spinning space stations from science fiction, like the wheel-shaped station in the film 2001. The physics is sound and it would work. But this classic approach comes with a significant and often overlooked drawback, a problem rooted in the very physics that makes it possible: the Coriolis effect. This effect introduces a disorienting twist to the simulated gravity. Because the spacecraft is a rotating frame of reference, the physics within it don't behave exactly as they do on a non-rotating planet like Earth. If an astronaut were to try to throw a ball straight ahead to a colleague across the rotating ring, the ball would appear to curve strangely, deflected by the Coriolis force. More critically for daily life, this effect plays havoc with the human vestibular system, the delicate fluid-filled canals in our inner ear that control our sense of balance and spatial orientation. In a spinning environment, the constant rotation can induce severe nausea, dizziness, and vertigo, making it difficult to walk, focus visually, or even feel truly stable. The larger the diameter of the rotating section, the weaker the Coriolis effect becomes, but building a spacecraft with a spinning ring hundreds of meters across is a monumental engineering challenge far beyond our current public capabilities. This leaves astronauts and mission planners with a difficult choice: endure the health-degrading effects of weightlessness, or suffer the disorienting side effects of the only known artificial gravity solution. It is precisely this frustrating compromise that would have driven NASA, a hidden research, to investigate a far more radical and seamless alternative: the creation of artificial gravity without any spin at all. The holy grail of this research would be the development of what we might call a gravity plate technology. Imagine the deck of a spacecraft not as a simple floor, but as an active surface that generates a uniform, one gravity pull directly downward, just like the ground beneath your feet right now. Astronauts would be able to walk, run, and live with complete normality, their bodies experiencing the exact same physiological stresses and cues as they would on Earth. There would be no disorienting spin, no curving trajectories for thrown objects, and no need for massive rotating structures. The spacecraft could be any shape, a simple cylinder or a box, and the artificial gravity would be contained within the habitable modules, a localized field of comfort and health. Achieving this would represent a quiet revolution in living in space, transforming a spacecraft from a precarious habitat where humans are constantly fighting their environment into a true home away from home, enabling missions that last for decades without detrimental effects on the crew. So, how could such a miraculous technology possibly work if not through rotation? Hidden research likely explored two primary avenues, one based on a clever application of known physics, and the other venturing back into the manipulation of fundamental forces. The first, more conservative approach involves continuous linear acceleration. If a spacecraft could accelerate at a constant rate of 9.8 meters per second squared, the equivalent of Earth's gravity, the resulting force would push the astronauts against the rear wall of the vessel, making it feel exactly like a gravitational pull. This is Einstein's principle of equivalence in action. The force you feel in an accelerating car is indistinguishable from gravity. The problem, of course, is the immense fuel requirement. To accelerate continuously for months or years on an interplanetary journey is far beyond the capability of any chemical or even nuclear thermal rocket. It would require a propulsion system of unbelievable efficiency and power, like the field propulsion or zero-point energy concepts we've already discussed. The gravity plate in this scenario would not be a magical device, but rather the indirect result of a revolutionary engine. The second, and far more speculative, avenue is the one that truly captures the imagination, the direct manipulation of gravity itself. This would mean finding a way to generate a genuine gravitational field using technology, not motion or mass. We've discussed the possibility of gravity manipulation for propulsion, but the same principles could be applied to create a stable, localized field inside a ship. This might involve the use of high-energy electromagnetic fields, exotic matter, or some other undiscovered principle to essentially bend spacetime in a controlled manner within the crew quarters, creating a gradient that pulls everything toward the floor. The power requirements for such a direct approach would be astronomical, again pointing toward hidden breakthroughs in energy generation. The development of a true gravity plate would therefore be a culmination technology, dependent on success in several other classified areas. Its existence would signal that NASA had not only mastered propulsion and power, but had also achieved a profound level of control over the most fundamental force shaping our universe. This single innovation would do more than just keep astronauts healthy. It would make the solar system feel a little bit smaller and a lot more like home. Hiding an object in the vast, empty expanse of space might seem like the easiest trick in the universe. After all, space is overwhelmingly black and unimaginably large. But this line of thinking misses a crucial point. The emptiness itself is the very thing that makes stealth so difficult. In the profound darkness, any object becomes visible precisely because it is not empty. It's the single grain of sand on a perfectly smooth black beach. The moment sunlight, starlight, or even the faint glow of zodiacal light strikes its surface, that object reflects that energy, creating a signature that can be detected by powerful telescopes and radar systems on Earth or in orbit. So, the challenge of cosmic stealth isn't about blending into a busy background like a chameleon on a leaf. It's about becoming a perfect chameleon on a perfectly blank canvas. To solve this puzzle, NASA, most secretive designers may have turned away from traditional engineering and looked instead to the masters of hiding in plain sight here on Earth, specifically to the creatures of the deep, dark ocean. The deep sea is the closest analog we have to the void of space. Sunlight cannot penetrate its depths, leaving creatures to live in perpetual darkness, broken only by the faint bioluminescence of other life forms. In this environment where being seen often means being eaten, evolution has crafted incredible solutions for invisibility. Some animals, like the ultra-black deep-sea dragonfish, have skin covered with microscopic structures that trap over 99% of the light that hits them, reflecting almost nothing back. This is the biological equivalent of vantablack, the human-made substance once considered the blackest black. A biomimetic stealth probe would take this principle to the extreme. Its hull wouldn't be simply painted a dark color. It would be engineered at the nanoscale with a forest of tiny pillars or cavities, a texture designed to catch incoming photons and prevent them from escaping. Instead of bouncing off, the light would be absorbed and dissipated as negligible amounts of heat, making the probe appear as a perfect, light-swallowing hole in space, virtually undetectable to optical telescopes. But true invisibility requires more than just defeating visible light. A probe must also hide from the prying eyes of radar and infrared sensors. This is where the concept of adaptive stealth comes into play, inspired by creatures like the octopus and cuttlefish. These cephalopods don't just have a static camouflage. They possess dynamic skin embedded with millions of pigment cells called chromatophores that they can control with their nerves, allowing them to change their color and texture to match their surroundings in real time. An advanced stealth probe would need a similar high-tech skin. Imagine a surface made of millions of tiny, programmable panels, each one acting like a pixel. On one side of the probe, sensors would constantly analyze the background, the inky blackness of space, the faint glow of a distant nebula, or the thermal signature of a nearby planet. This data would be fed to a central computer, which would then instruct each individual panel to adjust its properties. To evade infrared detection, the panels on the sun-facing side might actively cool themselves to match the frigid temperature of the cosmic background radiation, around -450 degrees Fahrenheit. Meanwhile, panels on the dark side might emit a carefully calibrated amount of heat to blend with the ambient thermal environment of deep space. This wouldn't be a single disguise, but a continuously shifting cloak, ensuring the probe remains a ghost against any celestial backdrop it encounters. The motivations for developing such an advanced capability are as compelling as they are varied. On one hand, there is the purely scientific desire for uncontaminated observation. If we send a probe to study the hypothetical subsurface ocean of Jupiter's moon Europa, we would want to ensure our presence doesn't alter the very environment we're trying to study. A stealth probe could enter orbit and observe for years without its faint electromagnetic emissions or its physical presence influencing the moon's delicate system. It could watch plumes of water vapor erupt from the icy surface without the risk of its shadow or heat affecting the phenomenon. This is the ultimate goal of a naturalist, to observe without being observed. On the other hand, the reasons are undoubtedly strategic. The ability to place an undetectable probe in a stable orbit around another world, or to hide one within the asteroid belt, represents an intelligence-gathering capability of immense value. It could monitor the activities of other nations' satellites, or act as a silent early warning system for our planet. The technology to make a spacecraft vanish would be as potent a tool for national security in space as stealth aircraft are in the skies of Earth. This concept of biomimetic stealth forces us to confront a profound and slightly unsettling possibility. For decades, astronomers have tracked countless near-Earth objects, asteroids and comets whose paths bring them close to our planet. The vast majority of these are natural, but the methods used to detect them, spotting a dark object against a dark background by the faint sunlight it reflects, are the same methods that would be used to detect an artificial stealth probe. This leads to a fascinating thought experiment. If a technology exists to make a spacecraft nearly invisible, and if that technology has been in development for decades, is it possible that our solar system is already being watched by silent, patient observers of our own making? Or, looking outward, if a civilization more advanced than ours has already mastered cosmic camouflage, could their probes be hiding in plain sight among the millions of catalogued asteroids, silently going about their mission, whatever that may be? The development of biomimetic stealth isn't just about building a better spacecraft. It's about opening a door to a new way of thinking about our place in the cosmos, one where the emptiness of space may not be as empty as it appears. Just as a skilled musician can tell if a cello has a hidden crack by the way it resonates when played, every physical object in the universe, from a tiny pebble to an entire planet, has its own unique natural vibration. This fundamental frequency is determined by its size, shape, density, and internal structure. It's the sound the object sings if you could strike it like a bell. Now imagine applying this simple principle on a cosmic scale. Instead of sending a fragile billion-dollar lander to drill a few inches into the surface of Mars, what if you could simply ping the entire planet from orbit and listen to its song? This is the powerful premise behind resonant frequency planetary analysis, a hidden surveying technique that turns a world's own vibrations into a detailed internal map. The method works on a principle similar to sonar used by submarines or the seismic surveys geologists conduct on Earth. A specialized instrument on an orbiting spacecraft would generate a powerful, precisely tuned energy pulse. This could be an electromagnetic signal or even a directed acoustic wave transmitted through a planet's atmosphere. This pulse is the ping. When it strikes the surface, the energy travels through the planet, sending vibrations rippling through its entire structure. Different materials and structures respond in different ways. A solid metal core will vibrate at a different frequency than a sloshing underground ocean or a vast, empty cavern. The spacecraft's sensitive detectors would then listen for the returning echo, analyzing the complex symphony of vibrations that come back. By carefully studying how these frequencies have been altered, which ones are amplified, which are dampened, and how long they take to return, scientists can reconstruct a stunningly detailed, three-dimensional picture of the world's interior, layer by layer. The scientific value of such a capability is almost immeasurable. For a world like Jupiter's moon Europa, which is believed to harbor a global subsurface ocean beneath a thick shell of ice, a resonant frequency scan could confirm the ocean's existence beyond any doubt. But it would go much further. It could map the thickness of the ice shell, pinpointing the best places for a future lander to attempt to drill. It could even analyze the composition of the ocean itself, potentially detecting chemical signatures suggestive of hydrothermal vents and, by extension, the possibility of life. When applied to an asteroid, this technology could act as a powerful prospecting tool, revealing the precise distribution of precious metals like platinum or rare earth elements within the rock, information that would be vital for any future asteroid mining operation. It transforms a mysterious, distant world from a single point of light into a transparent, cross-sectional diagram, revealing its hidden treasures and geological history without ever touching its surface. The strategic reasons for classifying such a powerful survey tool are compelling. In the new era of space exploration, knowledge of a celestial body's resources is the ultimate strategic advantage. If one nation's space agency knows exactly where to find the richest deposits of water ice on the moon water that can be converted into rocket fuel, they can establish a permanent, self-sustaining presence there long before their competitors. If they have a detailed internal map of a near-Earth asteroid loaded with valuable minerals, they can quietly plan a mining mission that would grant them economic dominance in the new space economy. Revealing that you possess this technology would be akin to showing your entire hand in a high-stakes poker game. It would alert every other spacefaring nation to your capabilities and your intentions, prompting them to accelerate their own programs and potentially contest your claims. By keeping resonant frequency analysis secret, an agency can conduct a comprehensive, silent inventory of the solar system's resources, identifying the most valuable assets and planning their exploitation with a decisive, unshared head start. This quiet mapping of the final frontier may well be the first and most important step in the great resource rush that will define the next century in space. But perhaps the most forward-thinking aspect of these cognitive suits lies in their predictive capabilities, moving beyond simple monitoring into the realm of proactive intervention. Imagine a system that doesn't just tell an astronaut they are stressed, but one that can predict the onset of cognitive fatigue or an error in judgment before it even happens. By establishing a detailed baseline of an astronaut's normal brainwave patterns during training, the suit's AI could detect subtle, pre-conscious deviations that signal a drop in attention or an increase in mental load. If the system detects the neural signatures of impending fatigue during a critical docking maneuver, it could automatically inject a mild, safe stimulant from an onboard medical dispenser or initiate a brief, targeted neurostimulation sequence to restore alertness. It could even intervene in more subtle ways. If an astronaut's neural activity suggests they are overlooking a crucial step in a complex checklist, the augmented reality display could gently highlight the missed item or present a simplified prompt. This transforms the suit from a passive monitor into an active guardian, a silent partner working in the background to keep the human operator at their peak performance, effectively creating a safety net made of algorithms and understanding, preventing small mistakes from cascading into mission-ending failures millions of miles from home. The development of such a deeply integrated system inevitably pushes us into profound ethical and philosophical territory. This technology represents the most intimate merger of human and machine we have yet explored, blurring the line between a tool and a part of the self. Where do we draw the line between an astronaut making a decision and the suit's AI influencing that decision? If the suit's neurostimulation is the reason a critical problem was solved, who receives the credit, the human or the machine? Furthermore, the constant biometric surveillance, while intended for safety, raises questions of autonomy and privacy. Does an astronaut have the right to disable the system if they find its interventions intrusive? The data collected by these suits would be a treasure trove of information about human performance under extreme stress, but it also represents a deeply personal neural record. The ownership and use of this data after a mission would need to be carefully governed to prevent its misuse for performance evaluation in a way that could be unfair or invasive. This technology forces us to confront a future where the very definition of human achievement may be intertwined with technological augmentation, challenging our concepts of individual prowess and resilience in the most demanding environment imaginable. Ultimately, the cognitive enhancement suit is not about replacing the astronaut, but about elevating them. The immense challenges of interplanetary travel, the isolation, the radiation, the delayed communications, the sheer complexity of survival demand that we send not just the best humans, but the best augmented humans. This hidden technology acknowledges that the limiting factor in our journey to Mars and beyond may not be the power of our rockets or the strength of our hulls, but the fragility and finite capacity of the human mind. By turning the spacesuit into a cognitive partner, we are not making the astronaut obsolete. We are giving them a technological extension of their own will, a system that amplifies their courage, sharpens their intellect, and safeguards their judgment. It is the ultimate expression of human-centric design, where the machine's entire purpose is to serve and enhance the unique, irreplaceable human spirit at the core of the mission, ensuring that as we venture into the great unknown, we bring the very best of ourselves along for the journey. Now, let's turn our attention to a technology that operates on a far smaller scale than terraforming planets or shielding entire spacecraft, yet its impact is no less profound. In the silent, airless environment of space, there is a hidden enemy that mission planners fight with relentless vigilance: friction. Not the familiar grinding friction of Earth, but a far more subtle and insidious kind. In the vacuum, there are no air molecules to cause drag, but within the spacecraft itself, in the gyroscopes, reaction wheels, and precision-pointing mechanisms that keep satellites stable and telescopes locked on distant stars, even the tiniest amount of mechanical friction is a relentless source of decay. Over years and decades, the microscopic wear and tear on a single bearing can cause a satellite to drift, a telescope's image to blur, or a probe's trajectory to slowly deviate, potentially ending a multi-billion-dollar mission. It is a battle against entropy itself, fought in the minuscule spaces between moving parts. To win this battle, a hidden technology taps into one of the most bizarre and counterintuitive phenomena in quantum physics, a principle known as quantum locking. The magic behind quantum locking, also called flux pinning, begins with a special class of materials, superconductors. When these materials are cooled to incredibly low temperatures, they undergo a dramatic transformation, losing all electrical resistance. But that's only half the story. They also exhibit another miraculous property: they become perfect diamagnets. This means they actively expel magnetic fields from their interior, a phenomenon known as the Meissner effect. Now, if you simply place a superconductor over a magnet, it will levitate, repelled by the magnetic field. But this levitation is wobbly and unstable. The superconductor can easily slide off to the side. Quantum locking is what happens when you take this a step further. Instead of a simple magnet, you use a magnet with a complex, pinched magnetic field, often created by a series of magnets with alternating poles or a magnet with tracks or grooves. When a superconductor is cooled and placed over this landscape, something extraordinary occurs. Microscopic magnetic whirlpools called flux tubes become trapped within tiny imperfections in the superconductor's structure. These trapped flux tubes effectively pin the superconductor in place relative to the magnetic field's landscape, not just vertically but laterally as well. The result is a form of levitation that seems to defy common sense. The superconductor doesn't just float, it is locked in mid-air with incredible rigidity. You can tilt the magnetic track, and the superconductor will maintain its exact position, hovering at the same angle without sliding down. You can even invert the entire setup, and the superconductor will remain stuck in place, seemingly glued to the magnetic field by invisible quantum threads. This isn't just levitation, it's a perfectly stable, frictionless magnetic bond. There is no physical contact and therefore no wear and tear, no energy loss from friction, and no generation of heat or vibration. It is a state of perfect, silent suspension. For the delicate machinery of a spacecraft, this principle is nothing short of revolutionary. Consider the reaction wheels that are the unsung heroes of satellite stability. To change a satellite's orientation without using fuel-thirsty thrusters, Engineers use these spinning wheels. By speeding up or slowing down the wheel's rotation, the satellite twists in the opposite direction due to conservation of angular momentum. But traditional reaction wheels rely on ball bearings, which, no matter how perfectly manufactured, eventually succumb to friction. This friction introduces tiny torques that cause the satellite to drift over time, requiring periodic corrections with thrusters that consume precious fuel and limit the mission's lifespan. Now, imagine a reaction wheel whose rotor is not supported by physical bearings, but is instead a superconductor, quantum-locked within a magnetic housing. This wheel would spin in a perfect vacuum, suspended by magnetic fields alone. There would be virtually no friction, no wear, and no gradual degradation of performance. The satellite could maintain its precise pointing for decades with microscopic adjustments, its fuel reserves preserved almost indefinitely. The benefits extend far beyond reaction wheels to the heart of scientific discovery, space telescopes. An observatory like the Hubble or the James Webb Space Telescope requires absolute stability to capture clear images of the deepest reaches of the universe. Any vibration, no matter how minute, can blur the image. The gyroscopes and fine guidance sensors that keep the telescope locked on target are especially vulnerable to the slow, insidious effects of mechanical friction. By implementing quantum-locked components, these critical systems could operate with a level of precision and longevity that is currently unimaginable. The subtle hum of microscopic friction would be eliminated, leaving only the pure silence of space. This would allow telescopes to observe fainter objects for longer periods, gathering data of unprecedented clarity and enabling discoveries that are currently beyond our technical grasp. It is this kind of behind-the-scenes breakthrough, a quiet victory over a fundamental physical limitation, that truly enables grand exploration. The decades-long journeys of the Voyager probes pushing into interstellar space were made possible by 1,000 such small engineering triumphs. Quantum locking represents the next evolutionary step in this silent war against entropy, a technology that ensures our robotic ambassadors to the stars can operate flawlessly not just for years but for centuries. Having journeyed through this remarkable catalogue of hidden technologies, from gravity-defying propulsion to self-repairing robotic explorers, it's time to pull back the lens and view this not as a random collection of secrets, but as a single, breathtaking tapestry. When we connect the dots, a powerful and unmistakable pattern comes into focus. This is not a scattering of disparate experiments. It is a deliberate, strategic assault on the four great walls of the prison that currently confines humanity to Earth. These walls are the immutable laws of gravity, the desperate scarcity of energy, the rigid arrow of time, and the profound fragility of our own biology. Each of the 22 technologies we've explored represents a concentrated effort to not just chip away at these barriers, but to shatter them completely. Consider the problem of gravity. It is the force that dictates the exorbitant cost of reaching orbit, that crushes our spacecraft with immense weight, and that makes long-term life in space a slow, degenerative illness. The hidden research reveals a multi-pronged strategy to conquer it. We see it in the Flux liner's attempt to manipulate spacetime itself, in the high-frequency field experiments seeking to create localized anti-gravity zones, and even in the more conventional but revolutionary pursuit of room-temperature superconductors that could enable powerful magnetic levitation. This isn't a single team trying one idea. It's a broad front campaign against the very concept of gravity as an uncontrollable force. The ambition is clear: to transition from being passive subjects of gravity to becoming active masters of it, turning the force that binds us to our world into the engine that propels us to others. Then there is the challenge of energy, the lifeblood of any civilization. Our current paradigm, whether chemical rockets or solar panels, is hopelessly inadequate for the scale of interstellar travel. The hidden portfolio, however, points toward a complete energy revolution. The pursuit of zero-point energy harvesting is the most audacious example, an attempt to tap into the infinite sea of quantum fluctuations that fill the vacuum of space itself. But it is supported by other breakthroughs, room temperature superconductors that would eliminate energy loss in transmission, and compact fusion or advanced fission reactors that could power the immense energy demands of plasma shields and field propulsion. The pattern here is a move away from carrying finite fuel to developing technologies that generate limitless power on demand. The goal is nothing less than the end of energy scarcity, a prerequisite for a society that operates on a galactic scale. The third great barrier is time itself. Both the limitations imposed by light speed delay and the biological clock of human lifespan. The hidden research addresses this with equally radical solutions. Quantum entanglement communication seeks to bypass light speed for instantaneous data transfer, effectively negating the communication lag that makes remote control across interplanetary distances so difficult. Consciousness interface systems take this a step further, aiming to project human presence across the solar system without the need for physical travel, conquering time by making distance irrelevant for the mind. And looking even further ahead, the theoretical work on exotic matter for warp drives and the designs for self-replicating von Neumann probes are investments in technologies that operate on timescales of centuries or millennia. This reveals an ambition that thinks not in terms of fiscal years or even human lifetimes, but in the deep, patient time of cosmic evolution. Finally, we have the vulnerability of the human body. Space is a fundamentally hostile environment, and our biology is ill-suited for it. The hidden technologies show a sophisticated two-track approach to this problem. One track focuses on transforming the environment to suit us, as seen in the radical plans for terraforming other worlds. The other, perhaps more profound track, focuses on transforming us to suit the environment. This is the domain of cognitive enhancement suits, biomorphic robotics that blur the line between life and machine, and advanced medical systems capable of synthetic biology and regeneration. The pattern is a move from simply protecting the fragile human form to actively upgrading and adapting it, ensuring that humanity can not only survive in the cosmos but thrive there. Underpinning all of these efforts is a unifying theme, the manipulation of fundamental physics. This is not merely about building better engines or stronger materials. It is about learning to command the forces that shape reality. From using metamaterials to bend electromagnetic waves for invisibility, to employing quantum locking to defy friction, to probing temporal anomalies with chronometric sensors, the research consistently pushes into the realm where engineering and fundamental physics become one and the same. This suggests a level of ambition far beyond what is visible in NASA public missions. The agency's hidden face is not that of an explorer content to send probes to take pictures. It is the face of a pioneer determined to rewrite the rules of the game, to achieve a mastery over nature that would elevate humanity from a species living on a planet to a civilization inhabiting a universe. These classified projects are not just secrets, they are the quiet, determined construction of a key to unlock the cosmos. These 22 hidden technologies are far more than just classified projects gathering dust in a vault. They represent something far more profound, a glimpse into a parallel timeline of human progress, a vibrant and ambitious technological future that is being actively constructed behind closed doors away from the public eye. What this reveals is a NASA whose true ambition extends far beyond the impressive but familiar missions we see on the news. This is not an agency content with simply visiting other worlds. It is an organization dedicated to a much grander goal, fundamentally redefining the very rules of exploration. They are not just building better rockets to travel faster within the existing constraints of physics. They are working to rewrite the constraints themselves, turning science fiction into science fact through sheer, determined ingenuity. While it is true that some of these concepts may, for now, remain in the realm of theoretical research or challenging experimentation, their very investigation sends a powerful message. It proves that the boundaries of what is possible are not fixed. They are elastic, constantly being tested and stretched in laboratories and think tanks that operate without public scrutiny. This continuous, hidden effort challenges every one of us to expand our own imagination, to think on a grander scale. It invites us to envision a future not where we slowly and painfully climb the technological ladder, but where breakthroughs so profound they seem like magic become the routine tools of everyday spaceflight. A future where the words "impossible" is retired from our vocabulary, not because we have given up, but because we have achieved a level of mastery over nature that our ancestors could only attribute to gods. This leads us to perhaps the greatest secret of all, one that transcends any single technology. The most astonishing revelation from this journey into the classified archives may not be the existence of a specific anti-gravity experiment or a working prototype of a quantum communicator. It is the overwhelming evidence of the sheer, staggering scale of human ingenuity that is being cultivated in the shadows. For every hidden technology we have discussed, there are undoubtedly dozens, perhaps hundreds, of other revolutionary ideas at various stages of development, each one a testament to the relentless curiosity and problem-solving brilliance of the human mind. This reservoir of untapped potential, waiting patiently in the wings for its moment to transform our world, is the true legacy of this secret work. So, what does this mean for all of us watching today? It means that the future is likely to be far more strange, wonderful, and advanced than any official roadmap would have us believe. The next great leap for humanity might not be announced with a press conference and a rocket launch, but it could emerge quietly from a decades-old program that finally reaches maturity. It encourages a sense of hopeful anticipation, a belief that the solutions to our greatest challenges, energy scarcity, disease, even the limitations of our own biology, may already be in development, their blueprints safely guarded until the world is ready for them. Now, we want to hear from you. After this deep dive into NASA's most secretive projects, which of these hidden technologies do you find the most plausible? Is it the practical elegance of quantum locking for frictionless machinery, or the world-changing potential of room-temperature superconductors? Perhaps you believe the evidence points most strongly to advanced research in metamaterials for active camouflage. Share your thoughts and reasoning in the comments below. Let's continue this fascinating conversation, and if you enjoyed this journey to the edge of known science, be sure to subscribe and hit the notification bell so you don't miss our next exploration into the secrets of our universe. Thank you for watching.